and we wanted to add it to -1, -1, 2. Might have run out a little bit of space. All right. All right. So then we just got to add 2 plus -1, or 2 minus 1, right? 2 plus -1 just becomes 2 minus 1. And then we get -3 plus 2. Right? Just add the respecting components. 2 minus 1, does that give me 1? -3 plus 2, I believe that gives me -1. All right. So that wasn't too bad. What I boxed in blue is the answers, right? So that's the new vector we got when we added them. All right. So let's go back to red color ink and let's go ahead and subtract them. So we have an idea already how to perform this operation. So we have our vector u up here and we have our vector v here. All right. So let's go ahead and subtract them. All right. X component of vector u was 2. Then x component of v was -1, but it's minus because that's part of the formula. So minus 1. Then we have, that's going to end up becoming positive, right? It's going to become positive. Then we have -3 minus 2 gives me, so 2 plus 1 is 3. And then -3 minus 2 is -5. So look how easy this is. This is not difficult at all. This is not difficult at all. And then next we have a scalar multiplication against vector u. So that's why I call this baby physics. All right. 2 times, and with scalar multiplication, it's kind of like distributing. 2 times 2 is 4, so we get a new horizontal component of 4. 4 times negative, 2 times -3 is -6. So now we have a -6 as a vertical component now. Very easy, very easy. When it comes to simple operations between vectors u and v. Now let's worry about -3 and then the scalar multiplication with the sum between them. -3, it's going to work exactly the same thing. Just to recall your memory, vector v was -1, 2. All right. So let's go ahead and, I did not need to do that, right? I could have just wrote -3, -1, 2, multiply by -3 each respective component. That becomes +3, right? It should become +3. And then -3 times 2, that should become, is that -6? We should get -6. -6. All right. No, I went backwards on the colors, right? I was doing red and boxing in blue. No, I'm writing in blue and writing in red and boxing in blue. I was writing in red earlier too. All right. Next is going to be 2 times u plus 3 times v, and we already got the idea of what's going on here. Pretty straightforward. But keep in mind, 9.2, we're going to see some tricks. You're going to be, where are sines and cosines at? They all disappeared. No, they'll come back. 2 times 2 gives me 4. 2 times -3, that gives me -6. -6. Plus 3 times -1, that gives me -3. 3 times 2 gives me 6. All right. And then now we just got to add each corresponding x component. 4 plus 4 plus -3. That's just 4 minus 3, which is 1. Right. Then -6 plus positive 6 looks like they're opposites of each other. So we get horizontal component 1 with a vertical component of 0. So not too bad. Just multiplying, add, and subtract, right? Add and subtract. So vector operations seem pretty straightforward when there's no trig involved. It's just like multiplication, just like anything we've seen in grade school. And now this next slide is going to come up with all the rules. All the rules that we have for vectors. The following properties of for the vector operation can be easily proved from the definitions. This is not a proof-based class. It says a zero vector is whenever we end up with a vector that has a horizontal and vertical component of 0. So that makes sense why that's a zero vector. It plays the same role for addition of vectors as the number 0 does for addition of real numbers. So adding 0 to any, like my favorite number is 15, adding 0 to 15 does nothing. It stays 15, right? It stays my favorite number. Okay. Here we have properties of our vectors for addition and multiplication. Believe so. All right. The reason why they don't have one for subtraction, because subtraction can always be rewritten as addition. It can be plus -3. So that's why we just see addition and multiplication. So some of the same rules apply, right? Like, for example, 3 plus 2 is the same thing as 2 plus 3. You get 5. So it doesn't matter what order you add the vectors, you still get the same thing. So this slide is just pretty much going over the rules of vectors, the rules we have, which are very similar to the rules that we use in algebra. So first one looks like the commutative property. Second one looks like the associative property. Third one looks like the identity property. As I'm going down here, one, you don't have to count and label them if you want. Third one looks like the identity. You add 0 and stays the same vector. And that's not the best choice of color, right? I'm just labeling 1, 2, 3, 4. Number 4 was just if you have opposites, a vector, and it's the same vector but opposite, obviously you're going to get 0, a 0 vector. All right. Then they have multiplication for scalars. So same thing, same rules apply. See the C right here? Looks like they distribute it. So here we have C was vector U and C was vector V. Same thing applies if the number you just, same thing applies if we have two numbers. You can distribute the vector to each respective number inside. All right. Now we have, this is another property we have here. This looks like a, what is this, associative property? It looks like a associative property for multiplication of scalars against a vector. So it doesn't matter what order you multiply the scalar against a vector. You can multiply the scalar D first against a vector and then C, or you can multiply the vector by scalar C and then by the scalar D. So if you have two scalars being multiplied by the vector, you can multiply whatever scalar you want first. So that's what they mean. And then they go on to talk about the identity. The identity for multiplication was 1. Anything times 1 is that anything. So 100 times 1 is 100. So it's the identity, gives you back yourself. 0, right? Anything times 0, 0. And a scalar times 0 will still be 0. So just some rules we have here. And then this one was straightforward. If you have a length of a vector, and that vector is being multiplied by a scalar, just go ahead and take the absolute value of both of those particular values and multiply them, and that would give you the length of the vector. Right? And it straight up says the length of a vector. All right. So let's work with our first example. So we have a vector. What do we have a vector here? So, all right. Now we're going in terms of I and J. All right. So a vector of length 1 is called a unit vector. for instance, the vector W has 3/5 and 4/5 as a their horizontal vertical components, is considered a unit vector. They say two useful unit vectors are I and J. So they tend to use I and J when we're talking about unit vectors in this case, right? So you notice on the I, he has one as a horizontal uh, component. Notice J, he deals with the vertical component, and we have one on the second coordinate, and we have an illustration there on the bottom there. So we see that I has a horizontal component of 1, 0 for vertical, so that's why it doesn't hop anywhere up. And then as for J, he has one unit going up. So looks like we could, form a right triangle we liked, right? So, and we could find, the distance between the endpoints between J and I if we like. So it's very interesting, right? Very interesting what we see here, how the Pythagorean the theorem keeps on coming up in this class. All right. So based on that information, it says these vectors become special because any vector can be expressed in terms of them. So here, let's say the vector v with horizontal components A and B in general can be expressed as the following. So here they go ahead and slap I with the horizontal component, and they slap J with the vertical component. All right. So if you're noticing why they have AI and BJ there, just remember I is associated with the horizontal component. J is associated with the vertical component. I did not choose the choice of letters. Mathematicians long ago did. I did not choose AI or BJ. I did not choose those. But as for everything else, it still looks like a Pythagorean identity. The Pythagorean theorem would work. So it still looks like a right triangle. So it doesn't look too difficult. Now we have I and J being slapped on, which are unit vectors. And let's see what's going on. Let's see what's going on. Let's play with it. Let's play with it. We see it. We vaguely understand it. But once we play with it, I think that's when we truly see how the formula works out. All right. So it says here, it says write vector u, which has 5 and -8 as its components in terms of I and j. All right, so that one's like there's no magic to that. Simply just simply slap the I and j to the 5 and the -8. So for A, there's not much you can do. It's just getting used to that. So I'll try to bold as possible. Do I have more colors? Do I have more colors? Collapse ribbon? No, no collapse ribbon. What is this? Select ink. No. Modify too. More colors. Oh, there was one right here. Modify too. Let's get rid of this pencil. I want dark. I want a dark pencil. No, I don't want a dark pencil. More colors. Yeah, it writes like a spray paint pencil. So looks like I'm stuck with 3 colors: red, green, blue. Those are the OG colors. All right. Well, I guess I'll use green for bold. Anything that needs to be bold, I'll stick with green, I guess. But all right. So or red, no, doesn't matter. We'll start with we'll use red for bold. All right. So here we have some scalar 5, and then a bold eye. That was it. That was pretty much it. And then plus our vertical component was -8, so you can do that -8. J, right? And that's it. So all we have is we have 5 minus 8, and then don't forget our ij. That was it. That was it. Right? And that's all we have to do. They want us to write them in terms of I and j, and that's all we do. We just left an I to the horizontal and j to the vertical component. Now in B they say now if vector u and vector v have those particular, okay, if vector u has horizontal component 3i and vertical component 2j, and vector v has -1, technically if they put -I they mean -1 of a horizontal component plus 6j as a vertical component. They want us to write these vectors in terms of I and j. They want us to multiply vector u by 2, a scalar 2, and vector v by a scalar of 5. And once again, terms of I and j. So that's not a big deal. We know how to multiply and we know how to write the letter I and j. So the properties of addition and scalar multiplication of the vectors shown show that we can manipulate vectors in the same way as algebraic expressions. All right, so let's go ahead and do that. We have 2v plus 5v. So let's go ahead and just write this like a algebraic expression. I don't know why I wrote positive 2. It's already assumed to be positive. All right, we have 2 and vector u. I thought I saw a check come in. Sorry. All right, so then 2, vector u from the previous page, u was 3i plus 2j. So 3i. I know I wanted to emphasize the differences between the scalars and I and j by bolding, but we'll roll with it. We'll roll with it. We keep in mind I and j are bolded. All right, plus 5 times the scalar v. The scalar v happened to be, the vector v happens to be -I plus 6j. That's just negative. That's just -I. That's just -I. -I plus 6j plus 6j. All right. And then just treat this like any algebraic expression like they just mentioned. Distribute. Here we get 2 times 3i. That gives me 6i. All right. 2 times 2j gives me 4j. 4j. All right. I'm gonna keep them in parentheses because I still need to do the vector addition, right? And I have to the vector subtraction, right? X2 minus x1, or in this case adding, adding, not x2 minus x1. That's to find the horizontal component. I need to add at the very end, so that's why I'm still separate them in parentheses. I still need to add the x components respectively and the y components respectively. Here we get -5i, parentheses -5i. And then here we get, is that going to be 30? Right, that gives us 30j. 30j. All right. And then next is just to add the respective x components at the x. Before when I said x2 minus x1, I was talking about finding the components. We already know how to find that. That was earlier in part 1 of this section. Here we're continuing on. Here this gives us a vertical component of just I. 6 minus 5 is 1. So here we just get I. And then next we go ahead and add 4j plus 30j, which gives us plus 34j. Plus, I can write that a little bit small. I can write that a little bit down below. So here we get I plus 30. Well, that's a weird 30. 4j. Excuse my J, right? That's a weird looking J. That's still looking weird. All right, that's as best as I can make my bold J. So that is our final answer here. So it looks like the properties of algebra follow just exactly what I was saying in that previous box earlier in the blue, right? The same, some of the same properties that we have for algebra, we bring them along into scalar multiplication and addition. Keep in mind, not all rules apply. Some do. It looked like a lot of them did. I'm glad that we were able to use algebraic techniques to help us solve vectors. Moving on, we're almost done. So here we ended up with I and 34J. Do we talk about plotting that? No, but we could plot that if we want. We go 1 unit to the right from the origin and then 34 units up. So we could do that, and then we can connect the right. We can the initial point of the first vector to the terminal point of the second vector, right? And then we can completely draw this vector geometrically. We can geometrically draw this vector. Now, what are we talking here? Ooh, now we're talking about trig. So here's the trig that I was talking about. And remember, it doesn't shock me, or it shouldn't shock you or surprise you, seeing cosine on the x-axis, right? Didn't cosine associate with the x value on the unit circle? Sine was associated with the y value of the unit circle. So it shouldn't shock you seeing cosine there on the x-axis and sine on the y-axis. So that shouldn't be a big shocker there when I slapped on trig now, right? And remember, if you're working with angles, make sure you're in degree mode, because we could actually solve for the angle, right? The angle between the positive x-axis and that vector there, right? We can solve for that actual angle there, but be careful, you would need to be in degree mode. So they said let V be a vector and the plane was the initial point at the origin. The direction of vector V is theta, right? It's determined by its theta. They say it's the smallest positive angle in the standard position formed by the positive x-axis and the V. They're just saying that angle is formed by, the vector line that far away from the origin, right? So formed by that angle. So sounds a little bit confusing, but not too confusing. As we see the illustration, we see the vector there. They're letting us know some information that we could find a horizontal component and vertical component if we knew the vector V and the angle. So we know that we could actually solve for the horizontal and vertical component. And I think that's what they want us to do. Yes, exactly. Yes, they're going to actually want us. This is technically A, and this is technically B, isn't it? Right? Isn't it? What we've seen before, right? We saw that. Where we saw? We saw that at the very beginning. What we started with, very beginning, first slide, very first slide. Do you see the connection now? So we see that in the very first slide we started with today. So technically that side is A and that is B. Brings us to our formal definitions. They say if we know the magnitude, which is the length of the vector, and the direction as well, then figure 14 shows that we can find the actual horizontal and vertical components according to the following formula. And then once we find those components, they go ahead and slap that I and J like we were talking about to let us know that those are the horizontal and vertical component. So we have our two main formulas here, which were also given on the previous slide. So to find A, we need to know the magnitude and the angle. Do cosine of that angle, we should be able to find the horizontal component. Similarly for B, the vertical component, we'll use sine instead. All right, and then thus we can express vector V in terms of I and J as follows. So it's not too bad. I know it builds, but they're not too difficult. They're not too difficult. So let's take a look. Hopefully they give us the length of the vector and they give us the angle on the next slide. So let's see what we have here. Maybe we were not leading up to it, but what does we have? What does the question state? All right. So a vector has a length of 8 and a direction of pi over 3. Remember, pi over 3 is the angle. So in this case, it's in radians. So We can be in radians. That's okay. They gave us in degrees. Pi over 3, that I believe is what, 60 degrees, I believe. Pi over 3, 60 degrees. So find the horizontal and vertical component. Ooh, there we go. That's the big hint. There we're gonna have to use the formula that we saw previously. Find the horizontal and vertical components given that we have a vector of length A and an angle of pi over 3. All right. So write V in terms of I and J. So that's okay. We know how to do that. We'll just slap the I and J at the very end. We'll wait for B to read in a bit. Now, hopefully somebody can help me if they have that calculator with them, their trusty calculator. So here, let's go ahead and find component A. Component A was the magnitude times cosine of that angle. We know that to find A, it's going to be the magnitude, which was 8 times cosine of the angle. So here I should have put magnitude is equal to 8 and theta is equal to pi over 3. All right, so now we'll do cosine of pi over 3. And let me know what you get. And then also, I want to set up the other one. All right, we can put this in blue. We like B is going to equal to 8 times sine, and again, it's the same angle, sine of pi over 3. So 4 is correct. Absolutely. 4 is correct. As for our second one, yes, I was about to say it's going to give you some decimal if your calculator doesn't give you exact form. Since let me fix this pi over 3 to give myself some space. If your calculator can give you an exact form, that'll be nice because that's what we look for. Unless they ask for decimal points, which would be more likely in a engineering course. So hopefully there is a way to have your calculator give it to you in an exact form. Or we could actually, I need a new slide. I could do it mathematically by hand. All right, if you like. All right, so let's close this. Unit circle, where's my unit circle? Pi over 3 was 60 degrees, like I said. Sine was the root 3 over 2. You don't have to write this down, but I can show you. So we had 8 times root 3 over 2, and we're supposed to end up with 4 square root 3. All right. So yeah, that's pretty easy. Just half that, right? 8 divided by 2 is 4 square root 3. All right. Cosine of pi over 3. Oh, sorry, sine of pi over 3 gives me 4 square root 3. All right, so that wasn't too bad. So that's where the 4 square root 3 comes from. So that wasn't too bad to algebraically do it by hand. So thus, vector V, right? Bold it as best as I can. Vector V has horizontal component V, vertical component of V4, vertical component 4 square root 3, and that's good. 6.93. That lets us know we're moving about almost 7 units up. Almost. We're moving about 6.7. We have a vertical component about around 6.93. Thank you for giving me decimal. That's good. And all we have to do is slap I and J. So for I plus 4 square root 3 J. Sorry with my eye. I tend to curl my eyes too. All right. So now we have found our new, we have found our horizontal and vertical components for vector V. All right. And then in B, let's go ahead and find B. B, where's B? All right. B says there's so much right and right. Where's the question? It says find the direction. Okay, find the direction. So it looks like they want us to find the angle. Find the direction of a vector that has -3 as a horizontal component and J as a vertical component. Now, when they say J, they mean 1J, right? 1 unit up. So here you could do a rough sketch. You could do a rough sketch, square root 3. Square root 3, what is that? That give me something relatively small, right? 1 point something, 1 point something. So think about it. You're going -3 units to the left, and you're going 1 unit up, 1 unit up, right? So let me see. Let's see if I can get my calculator. How do I do square roots on my calculator? All right, so we have 3 square root to 1.73. Yeah, so that's not good. Well, that gives us an idea. Square root 3 is about -1.73. So we moved about -1.73 units to the left. So like I said, in mathematics, we don't like decimals unless told otherwise, but that gives you an idea. That helps us give us an idea of how much we move to the left, but we'll leave it as square root 3. We'll leave it at square root 3. Come back to me drawing. Please come back to me. There we go. Let me draw. Let me draw. There we go. There we go. So that's all I wanted to demonstrate, that we move -3 units to the negative square root 3 units to the left, 1 unit up, 1 unit up, because we were dealing with vector u, which was negative square root 3I plus j. All right. So they want to find the angle. They want to find the angle. So let's go ahead and do that as follows, right? So here, wind friction. We weren't doing wind friction. All right. So where is that formula? Let me see. What slide was it? Let's see. If it's not from this slide, it's not from this slide, then it's from chapter 8. It's from chapter 8. Just briefly, quickly going over this magnitude formula, properties, examples, different properties, examples. All right, horizontal, vertical components, and then they want us to find the direction. All right, so. All right, so this was in chapter 8. I'm not too sure if anybody recalls that. Chapter 8, when we're converting from polar to rectangular to polar, one of them, one of the formulas presented to find the angle, I believe it was I believe this was converting from rectangular to polar. I don't know if this formula looks familiar. I believe this is from 8.1. 8.1, when we were transforming our x and y coordinates into terms of r and theta, r and an angle. They gave us a formula to find r, right? r squared was equal to x squared plus y squared, right? I believe that's the formula for r. And then they've said to find the angle to find the angle, we use tangent of theta is equal to the ratio y over x. So this is coming from 8.1. This is coming from 8.1. I believe we know y. We know y to be 1 unit up, right? Right? Isn't y equal to 1? Isn't y equal to 1? And then what's x equal to? Right? Didn't we move square root square root or 1.73, right? Units to the left, or square root 3 units to the left, negative square root 3. All right. So here we have tangent of theta, tangent of theta. That gives me 1 over negative square root 3. All right. Okay. Now remember, we don't like square roots. We don't like square roots on the bottom. So let me just simplify this a little bit more. Here we have 1 negative square root 3. Let's multiply by square root 3 over square root 3. That gives me a square root 3 in the numerator. This is all going to be negative, so it's okay. I can breathe the negative in the front. This is going to be square root 3 times square root 3, which is square root 9. Square root 9. Just multiply the 3's against each other, assuming the numbers are positive. I believe we know what the square root of 9 is. That's going to be 3. So therefore, this equals negative square root 3 over 3. All right. Now the idea is, so now we're down to this. I might need to make another slide. We're down to this. All right. Now, if we do tan inverse, what does that give us? Anybody want to do tan inverse of negative square root 3? Or I'll do it on my side. I'll do it on my. Anybody? Nancy?
Negative 45.
Negative 45. All right, negative 45. So you got negative 45?
Yes, sir.
When you did tan inverse?
Mm-hmm.
Okay. All right. So that negative 45 would lie around here, though, right? So that's almost correct. That's almost correct. So that's what we need to be careful when we do inverse of particular functions, because there's more than one answer or more than one angle that gives us the answer, and we have to respect the domain and range for these particular inverse functions. So that's why
Yeah,
it gave,
negative 30 now. I think I messed up the parentheses on the calculator.
no, but it makes sense what you had given me here
Okay.
because the domain, I think the range is only between pi over 2 and negative pi over 2. So notice how it gave you this red line here, negative 45 degrees. Because the domain, the range can only be from here. So that's correct. That's correct. Another way we could have done it, because the calculator is only doing what you're telling it to do, right? We had to, if our vector was down here, that would be perfect. And the angle would be negative 45. Somebody said negative 30? It should be negative 45. Should be negative 45. Should be negative 45. All right.
I don't know.
Careful.
I did it again, but I put like the parentheses on the calculator, and it gave the first time it gave me negative 45, and the second time it gave me negative 30.
In degrees or radiant mode.
Yeah, in degrees.
You should be in radiant mode. Notice how this is in radiant?
Okay.
Yeah, if it was in degree mode, if they gave us an angle that was in 60 degrees, then we would be in degree mode. So in radiant mode, you got negative 45? Yes?
I got a decimal in radian mode.
Yeah, but you got negative 45 though in radians. Cut. The whole point I want to illustrate another way is got to be careful when we do inverse. Here we're pretty much trying to do tan inverse of negative square root 3 over 3. Now we could look at the unit circle. I don't think this is a unit circle. Oh. All right, so this is negative square root 3 over 3. Obviously, we don't see that here. We would have to take the ratio y over x to see which angle would give us that. So I noticed someone said negative 45 degrees, which maybe I've been a little bit wrong, right? That was, you said negative 30. Yeah, negative 30 is the correct one. Yes, good, negative 30. So yes, negative 30. This goes along negative 30 right here. This is negative 30. So that makes sense. That makes sense because tan inverse, his range is in between this part right here. So yeah, you are correct. It was negative 30. All right. So be careful. Negative 30 technically is correct, but that's in the opposite direction. Remember when we had negative radius, we go in the opposite direction. So this one is actually over there. It's actually an angle. If we follow the unit circle, if we follow 30 degrees, negative 30 degrees, this is negative 30. It goes along 5 pi over 6. All right. But another way to solve for this is the reference angles. So be careful with the tan inverse, right? We were here, and we continued on to the next slide here. They gave us some information. They gave us some information
The
here.
answer supposed to be in degrees or radians?
Radians, because this is in radians.
Yeah, okay. Just making sure.
Mm-hmm. Yeah. Now they gave us, if the angle happened to be in degrees, then we would have to be in degrees. It all depends on what the presentation of the problem. So another way you can do that, because when you do tan inverse, it gives you in respect of its range here. But we know tan's range is over here, but our vector is in quadrant 2. Our vector is in quadrant 2. So it's okay. That gives you an idea. That gives you a better idea. You just go in reverse. So if you got negative 30 degrees, just go in reverse and look at that. Look at that. That's weird. Negative 30 degrees, right? You must have been in 30 degree mode. Well, that's strange. Anyways, they told us the angle. The angle was, what was the angle again? Pi over 6. What was the angle? What was the angle? Pi over 3. Pi over 3 was the angle. All right. So power 6. Power 6. All right. Reference angle of power 6. How do they get that? All right. So let's take a look at this. 1/2 over. All right. Let's look at the power 6. Well, let's look at 5 power 6. So 5 power 6 says some of you may have got negative 30 degrees. Technically, this is negative 30 degrees, but that's in the negative direction. If you follow along, that gives us the 5 power 6. All right, so let me take the ratio of 5 power 6, 1/2 over negative square root 3 over 2, and hopefully it gives me this right here. Because then I have the right angle because I'm in quadrant 2, and I have 5 power 6 as my angle. So I think I said 1/2 over negative square root 3 over 2. All right, so that gives me 1/2. Change, right? Flip, right? Flip, right? Flip, keep, change, flip. Negative 3, that's okay. Choose cancel out. 1 over negative square root 3, yes. This looks like it's working out. Multiply by square root 3, square root 3. It gives me negative square root 3. And that's going to be square root 9. Square root of 9 is 3. So awesome. It looks like the angle. So the angle 5 pi over 6 looks like it works because the angle 5 pi over 6 tangent of 5 pi or 5 pi over 6 gives us a negative square root 3 over 3. Little tricky, because if you take tan inverse like we're used to, it's going to give you in the negative direction. It gives you this one. It gives you negative 30 degrees, or in this case, it should have gave you, if you have a calculator that gives you exact form, it should have gave you negative power 6, negative pi, power 3. Should have given you negative power 3. It should have gave you negative power 3, which is negative 30 degrees. So, but again, remember, this is in the quadrant 4, but the information set up for us in the beginning of the question told us that vector u was in quadrant 2, So knowing a little bit of the information, I knew about 30 degrees. I followed along my unit circle, and I found that 5 pi over 6 was a good candidate. I went ahead and double check right here where I'm checking mark. I double checked there to see if the ratio y right here. This is where I started. I checked if 5 pi over 6 works. So it looks like our angle is 5 pi over 6. So again, the idea was, and I know most of us don't like working with inverse. So the idea was to get tan theta So the idea is for what angle would give me, for what angle of tangent would give me negative 3 over 3. And we see that the angle 5 pi, the angle 5 pi over 6 gives me negative 3 over 3. Yes. So technically, if you had used 11 pi over 6 or negative 30 degrees, technically you would have been correct. But you would have been in the wrong quadrant. So a big hint to let you know which quadrant you or which angles you should be working with is where are you exactly? So in our problem, we were already in quadrant 2. So they let us know that we went this is not to scale, but we went negative square root 3, right? Negative square root 3 units to the left and 1 unit up. And they said the vector was here and they wanted to know the angle. So that they gave us a big hint there. So that big hint says we should have been looking at these angles here. Those angles in quadrant 2. So that's what I said. Be careful when you do tan inverse, sine inverse, and cosine inverse. Yes, they generally will give you the correct answer, but you have to respect on which quadrant you're in. So those of you who took tan inverse, that's good. I'm glad you have your calculator with you. You're coming prepared to class with your calculator. But be careful. Each inverse cosine, sine, and tangent have his own respected domain and range. So let me see if I can pull that up real quick. We're done with this section, almost done with time. So elaborate a little bit more on this problem. I thought it was going to be a little bit straightforward in finding the angle, but it took me a little bit to explain it. Hopefully it made some sense. So let's go back to chapter 5. Let's go back to chapter 5. I believe it was 5.5. What section is this? Inverse. So let's look for inverse tangent. Inverse tangent. All right. This cancellation properties. Moving forward. Okay, it's right here. See, a tangent inverse, his domain is all real numbers. So x for all x's are fine, but we have to be careful for the range. For the ranges from negative pi over 2 to pi over 2. So notice how all this information is combining on each other, piles, right? Is the foundation to building, our well knowledge of mathematics, like a house, needs a foundation to build the house up. So we need some foundation to build our mathematical skills, right? So that's why this right here, some of you got maybe negative pi over 3 or negative 30 degrees, which technically is correct, but our vector is in vector 2, so that vector quadrant 2, so that should give us a big hint that we should go in the opposite direction. Does that make sense now? Did that clear any confusion on why we went with 5 pi over 6 instead of negative 30 degrees or negative pi over 3? Okay. Somebody else from the regular people that speak up. Okay, perfect. Thank you. Because yes, be careful. Like I said, when you take tan inverse, cosine inverse, it's gonna give you the right answer, but then we just gotta respect what quadrant we're in. So remember your tan, cosine, and inverse. What's in his in his range? I'll go back right here. This is the range right here in red. This is the range for tan inverse. So that's why that's why this one we could not go with that. We could not go with that one, that negative 30 or negative pi over 3. All right, that's the range for it. All right. All right. So wrap it up. Sorry, I was drinking my orange juice. So yes, technically negative 30 does fall in the range of tan inverse, but our vector was in quadrant 2. Maybe I worded that wrong. I was thinking that in my head right now. I was taking a sip. Yes, yeah. Negative 30 does fall. Negative 30 degrees does fall in within the range of negative pi over 2 to pi over 2, but it's not in the quadrant we're in. Sorry, I think that cleans it up, wraps it up a little bit better. So this pretty much wraps up 9.1. 9.1. So I didn't like that the formula wasn't given. So let me go ahead and write that somewhere. I wrote it here first. So I'll go ahead and box this in. Box this in right here. So they ask you to find the angle between a vector and the horizontal and vertical component. That's the formula you'll be using. This was presented in chapter 8. I don't like how the textbook does not explain that, oh, we're going to be using the formula from chapter 8. They just go ahead and say, okay, use tan theta equals y over x and find out that 5 pi over 6 is your answer. That's pretty much what the textbook says. But here I try to break it down as best as possible here. All right. Okay. Now, we are done with 9.1. So we are finally done. I thought I would finish a lot faster, but uh, press escape keep to cancel save. No. Well, speeding things never gets the job done right. Right. All right. So we finished 9.1. 9.1. Let's take a look at what 9.2. Let's just see what it would show us. Am I logged in? Blackboard, please. Yes. All right, we'll just take a peek. We'll take a peek. We got about 5-6 minutes left. So let's see. So as I'm opening this up, how did you feel about 9.1? How did you feel about 9.1 so far? Out of the 52 people here. Bit challenging, straightforward, mixed results, mixed result. The angle might be the challenging part. Um, so what I would say for the angle is find out what quadrant you're in, right? So in this case, in our last example, what helped me a lot what helped me a lot to figure out that I am working with quadrant 2 right here is the whole fact from the question. Where is it? One has more than necessary. They gave us the actual they gave us the actual direction of the vector. Okay, okay, that's good. That's good that they explained why tan inverse when you take it. It gave us a correct answer technically, right? We're still gonna get negative square root 3/3, but it's gonna be in the wrong quadrant. So this one, this right here, the vector is letting us know the direction it's going. It's already letting us know the direction it's going. So, or at least the horizontal and vertical component in this case. So here, they went ahead and helped us with an aid of vector u, but at least we know this and we know this. All right. And they wanted to find this angle. So we're working with quadrant 2. We're working with quadrant 2. I know we set it up with tangent of theta to be y/x. Be careful. It was going to give you an answer that's down here, and that's not what we want. We wanted an answer that was up there, and that angle happened to be 5π/6. All right. Now they do reference angles. They talk about thus the reference angle is 5π/6. It wasn't obvious, and they say it follows that 5π/6 is the angle. That's not really the best. The best way. They didn't really explain the best way there because I really didn't know. I really didn't know this angle here, right? I didn't know that angle there. In order to find a reference angle, so let's see, pi/3. Erase. Let me erase anything. Oh, it's an enable editing. Okay, I can close this. All right. So just a little quick peek at 9.2. 9.2, a lot of multiplication going on as well. So now one of the first things we'll be looking at 9.2 is known as the dot product. So in this section, we'll do dot product. It's short. It's 21 slides. So it'll be best of when Friday we did a homework day or we do 9.2 on Friday. Let me know because Friday You can use that to catch up on homework. Like I mentioned, the grade book is now fixed. So as soon as you finish an assignment on Newton, it goes straight into your Blackboard. But for whatever grades you haven't or assignments you haven't done yet, no grade is there. But once the due date is passed, then it inputs a 0 there. So I believe I can cover 9.2 most of it on Friday, or do you want to keep Friday a homework day?
Homework.
Homework, lecture, Friday, homework day, lecture. Oh, some people have a history exam at 9:30. Oh, you have a test at the night. How do you have a test at 9:30 if homework day is nine? I won't get into that. I won't get into that. So a lot of you have an exam on Friday at 9:30. It's at 11 right after. Also, you would like to study, work on some homework. Okay. All right. Okay. Okay. Well, Friday. We'll leave that for homework day. All right. So just a quick sneak peek before I let you go. All right. Dot product. Now we know a little bit about vectors. Now we can have two vectors and then we can find the angle between the vectors. So that's what the dot product does. The dot product helps us find the angle between the two vectors. Little sneak peek here. So we'll be looking at dot product and work. So here is the first formula that we'll see the next time we talk about chapter 9. And we'll definitely be able to finish here. So again, it's just multiplying, um, multiplying cosine, multiplying, dividing. Some of them could be a bit tedious, but again, it's just multiplying. So yeah, this shouldn't be too bad. Alrighty. So we'll definitely should be able to finish this on Monday then. Oh, some have it at 11 and others at 9:30. So it would be a bit unfair if I lectured and some didn't have access to ask questions and some didn't. So and it would be small. Okay. Bit strange, but I'll respect that. I respect that. I won't rob you from your exam, right? I won't say, "Oh, make it to class, or you're gonna be absent." So okay, we'll keep with that. I'll work with you. Yes, that's what I'm wondering. Yeah, that seems a bit strange. Sometimes so what happens? Sometimes other professors don't know student schedules, so they schedule exams at times. Uh, okay. All right, just let me know. Just let me know. All right, just let. All right.
Yeah, because she said she's lecturing on Thursday, so we have to. The only time we can take the test is from 9:30 to 11. That's when the test will be open for the day, and that's all.
Oh,
Wait,
really?
9:30. She said 11 to 12:30. From what I remember.
It depends
She,
what
she
period
told
you
us
have her
she
in.
told
Like
us
some students
9:30
have
to
her at
11
9.
or 9:30 to 11:30. Yeah, she wants
Yeah.
us to take it all at the same time.
Yeah, I understand. I understand. That's how certain fields, and that's what I did in summer one, uh, on multiple time schedules. Yeah, yes, of course, should not conflict, but
That's why I was like, well, how are we? Sorry, we're supposed to like skip our other classes if we're taking the test.
okay. Usually that's not recommended.
Yeah, but that's
It-
the whole time
it's
the
just it's because when you sign up on any system, whether STC, TRGV, or any institution, uh, the system won't let you sign up for classes if they have time conflicts. So yes. Yeah. But if that's the only time, That's the only time. Um, we'll leave it as a homework day. We'll leave it as a homework day. Of not, I could record it, but I don't want to record it. I don't want to record it. Work, work, work. I mean, I could record this. I could record this, but it's a very, very short section. All right, so let's just keep Friday. Yes, it's very confusing with everything going back. So let's just keep Friday as a homework day. Let's just keep Friday as a homework day. Yes. All right. All right. We'll keep Friday as a normal homework day. Since this is such a short section, I might make a video or might not make a video over it and post it on Friday. So be aware for this. So all right. Well, we'll keep Friday as a homework day. I may or might not make a video over this and post it on Friday. So be aware to watch 9.2 if I do post it. So to clear the confusion, Friday will stay as a homework day. That good enough? Yes. All right. That'll clear some of the confusion. All right. Friday stays as a homework day. All right. And if necessary, I will make a short video over this section if necessary. So be on the lookout. Be on the lookout to all the announcements I make. So good luck on that exam. So we'll see you next time.